Hello. In this lesson, actually, let's start by just summarizing where we've been, and then we'll talk about where we're going. In the last few units, we've been looking at quadratics. We started by just looking how you add, subtract, multiply, and divide. We call that factoring with them. We looked at then how you graph them. You can graph by factoring. You can graph by using that the vertex's x-coordinate is always at negative b over 2a if it isn't factorable. And then we looked at if it was in a form called vertex form, you could plot the vertex and then use the steepness factor to get a few more points. So far we've looked at how you add, subtract, multiply, and factor quadratics, and how you graph them. What we're going to focus on in this last unit is how you solve quadratics. We've seen a little bit of it already with one tool, factoring, but there are a few other tools that are more efficient in some other cases, and so that's what this unit looks at doing. So moving forward, we're going to look specifically at how you solve quadratic equations where the biggest power is a 2. You've probably seen a little bit of this from prior classes, and so we're going to start with some warm-up questions of things you might have seen before. And so I'd like you to try the following 6 questions, see what you know. I'd like you to solve each equation for x. What value could you put in for x so that when you square it, you get 16? So pause the video now, unpause it once you've had a chance to try. Okay, welcome back. You might note that the value you're looking for here is 4, so we're going to start with just saying 4 because 4 squared is certainly 16. What about here? Well, that would be 3 squared. 3 squared would be 9. This would be 2 squared, and that's 4. X could be 1 here because 1 squared is 1. And then 0 would work because 0 squared is 0. But what if I told you for these first 4, you actually only have half the answer? There is another value because look, the biggest power is a 2. It tells you for most cases you're going to have 2 answers. Well, you could have had the negative as well. Look, negative 4 squared is also 16. Negative 4 times negative 4 makes 16. Negative 3 squared would also work. This one, negative 2 squared, would also make 4. This one, negative 1 squared, would also work. It would make 1. Over here, there's no such thing as negative 0, so this one only has one answer. What about this last one? You might try thinking, okay, I need to square a number and have it be negative 9. So some people try 3, but 3 squared makes positive 9. We already saw that. Maybe say negative 3. Well, negative 3 squared also makes positive 9. So it can't be 3 or negative 3. And now let's look at this again, closer. If you square something, it means you're multiplying it by itself. That number was either positive or negative. If it was positive, a positive times a positive is positive. If it was negative, a negative times a negative is positive. So here we would say there are no real answers. We use the phrase real because all the numbers right now that we know about are real, but you'll learn in future math classes that there are other types of numbers besides all the numbers you know right now. And so we call all the numbers that you know right now the real numbers. But right now there is no number that we know of that we can square and make negative 9. So we're going to look at expanding on this type of idea that we're using. Because really what we're going to look at is how do I get rid of a square? I could take the square root. The square root of 16 is 4 and negative 4. The square root of 9 is 3, and it could have also been negative 3 because of the squaring. So that's what we're looking at. To get the square root button on the calculator, I will show you. If you have a graphing calculator, it's going to be located right underneath the squaring button. It's in blue though. So you hit second, and then it looks like you hit the squaring button, but it's really the square root of 16. It will always give you the positive case. It assumes that if you're solving a quadratic, you know the second one would be the negative of that first number. And so here's the lead-in idea. In the last unit, we looked at finding the x-intercepts. How did we find the x-intercepts? Well, we said we wanted to be able to graph it to be able to find the x-intercepts and then the vertex, and then I could graph. We said, okay, we want y to be 0. Once y was equal to 0, we factored it. And we said, okay, we had 3x squared minus 27, and then because there was only 2 terms, we did greatest common factor factoring. What's the biggest number I can divide out of 3 and negative 27? Well, a 3. They both don't have x's, so I can't divide an x out, so I just am left with 3 parentheses x squared minus 9. And then I looked and said, hey, that's really x squared plus 0x minus 9. I can factor this more. I know 2 numbers that multiply to make negative 9 and add up to be 0. They're going to be 3 and negative 3. So my factors would be x plus 3 and x minus 3, and then I would go solving. I essentially have 3 things being multiplied here. I'm going to use colors to denote them because there's a lot of 3's going on. Red thing times green thing times blue thing, a long chain of multiplication equaling 0. One of these things has to be 0. Can it be the red thing? Nope. because that's just the number 3. But it could be the green thing. The green thing would equal 0 if x equaled negative 3. There's one of my solutions. And the blue thing would be 0 if x equaled 3. There's my 2 solutions. So I would say I know that the x-intercepts for that graph are negative 3 and positive 3. And then I think you hopefully remember by now how you go through the rest of that process. The vertex is halfway in between 3 and negative 3 is 0. I put 0 in the equation, and I would get negative 27 to find the vertex. So that's how the program is doing it here. Let's just check. There's 3 and negative 3, and then there's the rest of the graph for us. So that's what we focused on last chapter, was solving these equations by factoring and then graphing them by factoring. But this is kind of a long process. There's actually a much quicker way that I could have done this by using what's called a square root. A square root is the process that we use to undo a square. The steps are as follows. So instead of factoring to graph this, let's use square roots to solve. Step 1 is get the squared item by itself. What do I mean by that? I mean get the item that is being squared, so I'm going to put a box around it, by itself. If I want to get that by itself for step 1, you work away and towards it, just like when you solved equations back in the earlier part of the year. If I had 3a minus 27 equals 0, I would add the 27 over first. So I get 3x squared equals 27. I don't have the x squared by itself yet. I need to divide by 3. Now I get x squared equals 9. Now that I have the squared item by itself, I use square roots to undo the square. A square root will cancel a square. What do I mean by that? I mean, imagine I had the following statement. Square root of 5 squared. Well, I work inside and out, so 5 squared is 25, and then the square root of 25 is equal to 5. Look what happened. The square root and the squared canceled each other. It left me with just the lowest part, the base. That's what we mean by cancel out. They undo one another. It's like multiplying and then dividing. They're inverse operations. Square root of the x being squared will just be x, and the square root of 9 is 3 or negative 3. There's a little notation we can use, so we don't have to write 3 and then comma negative 3. We can put plus minus out front. So the two answers are positive 3 and negative 3. If you check by putting it in, let's put 3 in the equation and check. 3 squared is 9. 9 times 3 is 27, and 27 minus 27 is 0. So there's the first answer. Second one, get the squared item by itself. So that's p squared. Subtract 12 from each side. Subtract 12, subtract 12. I get p squared equals 0. Now I have this squared item by itself, and then I use a square root to solve. Square root cancels the square. I'm just left with p. The square root of 0 is the only time that you're only going to have one answer, because there's no such thing as a negative 0. So p equals 0 is the only answer for that one. Almost always you get two answers though. Last one looks like this. Get the squared item by itself. This is almost identical to the first one. Add 3 to each side first. 2a squared then equals 18. Divide by 2. I get a squared equals 9. And now this is just like the one we did a second ago. Square root, square root, square root of 9 plus or minus 3. So those are some good introductory examples of solving using a square root. There was the one that we talked about where it undid the square. Here's an example of using square roots where it might lead to a fraction answer, but that's okay, we can do it too. Fractions are numbers. Get the squared item by itself. I need to divide both sides by 4. And you could use a decimal here, but I'm going to leave it as a fraction. You're going to see why. Z squared equals 9 divided by 4. Then I'm going to take a square root of both sides. And watch what happens here. Square root square makes z equals, I'm going to have plus minus. Now watch. I'm going to use the calculator to help me before I realize what it did. If I type in the square root of 9 divided by 4, it gives me 1.5. Well, realize that 1.5, if you go to math and choose option fraction, it'll tell you what is that as a fraction. It's 3 halves. So it's plus or minus 3 halves. How did the calculator do that? Look, the square root of 9 is 3 and the square root of 4 is 2. If you have a fraction and both of those statements are perfect squares, you can just do the square root of the top and the square root of the bottom and get to your answer. That will always work. It's just this most helpful if both the top and bottoms are perfect squares. If one of them wasn't a perfect square, like if this was 11 over 4, you would just want to work with decimals then and write what the decimal answer is. But if they're both perfect squares, then I would write it as plus or minus 3 divided by 2. Last two, and then I'm going to have you try, is using square roots where you're going to have to use a decimal. Get the squared item all by itself first. So add the 11. 3x squared will equal 7 plus 11 is 18. Divide by 3, divide by 3. That leaves me with 6. 6 is not a perfect square, so when I take its square root, I'm going to have to use decimals because the square root of 6 is what we call an irrational number. It goes on forever and it never repeats, so we're going to have to just stop the decimal at some point to get an approximate answer. Here it's telling us to go to the nearest hundredth. That's to 2 decimal places. So square root of 6 to 2 decimal places is 2.4, and then this 4, the second one's going to get rounded up because behind it is a 9, so it's 2.45. Don't forget, plus or minus, because there's two answers because we're solving quadratics. Quadratics have two answers. They have two x-intercepts almost always. I guess the second one is for you to try. So I'd like you to try this second one. You're going to have to use a decimal because it's going to turn out to not have perfect squares with it. So pause the video now. Unpause it once you want to see how you did. Okay, first step is to subtract the 2. You would then get 5x squared equals 4. If you divide by 5, you'd have 4/5. And when I take the square root, the square root of 5 is not going to be a perfect square. So I'm going to need to use a decimal approximation here. So x equals plus or minus, I grab a calculator, square root, 4 divided by 5 to 2 decimal places, 0.89. There you go. Let's check, just to check an answer. 0.89. I should be able to do 5 times 0.89 squared, what was it, plus 2, and it should be very close to 6. It won't be exactly 6 because we had to round the 0.89. It'll be just below it because we had to round 0.89 to 0.890, and it was really 4.4. But 5.96, if you rounded it, would be 6. So, hey, it works out. Here's an example where we're going to use square roots, but we're going to have to split it into the two answers. So get this. This is why in the very first step I said when solving quadratics with square roots, it's get the squared. I said item. I didn't say variable. I said item because sometimes it might be a bigger expression that's being squared, and that's exactly what's going on here. I want to get this squared item all by itself. What's happening to this squared item? It's being multiplied by 2 right now. Do not distribute the 2 through. That's a common mistake. The reason you can't is because if I distribute the 2 into here, it's going to get squared. 2 squared is really 4, but it wasn't a 4 that was out front. So I can't distribute the 2 through because it would get squared and it wasn't originally squared. So that's where we say get the squared item by itself. Just divide everything by 2. I then have x minus 5 squared equals 9. Now I have the squared item all by itself. Take square root, take square root, and the square root of 9 is 3 or negative 3, which means x minus 5, because the square root will cancel the square, now the x minus 5 is by itself. That means x minus 5 either equals a negative 3 or x minus 5 will equal a positive 3, because that's the two things that x minus 5 could be, and it would be squared and make a 9, because negative 3 squared is 9 and positive 3 squared is 9. Now I solve for my two answers. Add 5. That means x either equals, if I add 5, a 2, or if I add 5, it'll be an 8. And I'll use Desmos to show you the picture to justify that our two answers are 2 and 8. And we could also check, besides using Desmos or a graphing calculator, you could just plug the numbers back in. Let's put 8 back in while we wait. 8 minus 5 is 3. 3 squared is 9. 2 times 9 makes 18. Here's that graph, 2x minus 5 squared, and we would need minus 18 to equal 0 so we could solve it. And if you look, there's our two x-intercepts, 2 and 8. It's the values that we got, so we did it right. I'm going to have you try one like that. So pause the video now for maybe a minute, minute and a half. Just make sure that you can do one like that. Unpause it once you've had a chance to try. Okay, welcome back. First step, get this squared item by itself. Divide both sides by 3. You will then get x plus 1 squared equals 4. Now how do you get rid of the square? You square root both sides. There are two answers though. The square root of 4 is negative 2 or positive 2. So that means x plus 1 either equals negative 2 or positive 2. Subtract 1, you get one of your answers, negative 3. Subtract 1, you get your other answer, 1. Go ahead and check. Let's check one of them. Let's check -3. -3 plus 1 is -2. -2 squared is 4, and 4 times 3 makes 12. It works. You can check with the 1. It will work as well. This last example that we're going to do uses the equation for parabolic motion. That's the motion of anything that moves through the air, projectile motion. If I could, I'd show you the video right now, but I think because it's being a recorded lesson, it'd have a hard time. It would buffer a lot when showing you a video. So this is a little video clip from the movie. It's like Journey to the Center of the Earth, I think is the name of it, or something like that. And in it, what he does is he drops the stick, and he can count how long it takes to hit the ground. And by doing that, you can estimate actually how high you are. And so in the video, I think he does something like it takes like 3 seconds in order for it to hit the ground. And so then what he does is he can estimate how high he is, because S is the final position. So the final position, if it hits the ground, to be 0, equals -16. He counts, and it's pretty close to 3 seconds if you watch the movie. So this would be 3 squared to be 9 now. Plus v is the initial velocity. If you just drop something, the initial velocity is 0 times 3 seconds. And then plus h. H is the initial height, and that's what he wants to know, how high he is off the ground. We don't know that. So then this is the part that he's kind of calculating right here in his head. -16 times 9. If you, well, you could do -16 times 10 and then just do one power or one group of 16 less than it. It'll be -144. 0 times 3 is just 0 plus h, and then you just add the 144 to the other side. So in the movie, he gives an estimate pretty close to like 144. I think he's actually a little off though. So they would say he's about 144 feet up. That's about 14 stories. So you can use a little mental math as long as you understand how quadratics work in order to estimate how high you are. So all you do is you drop something and you time how long it takes to hit the ground. And then the trick is actually you just take that time, you square it and multiply by 16, and that will tell you how high you are. So let's say you drop something, it takes 5 seconds to hit the ground. You listen for it to hit. You would square that. 5 times 5 would be 25, and then you do 25 times 16, and that would tell you that you're approximately about 400 feet off the ground. That'd be really high. What we're going to do is we're going to do one where we need to do the opposite. The question is going to be, how long would it take if you did this off the Golden Gate Bridge? So we're going to look up how high the Golden Gate Bridge is. So height of Golden Gate Bridge, and it's 220 feet. So we're going to go back to that equation that we had. The equation is S's position is equal to -16. That's just the value for Earth, negative because gravity pulls you downward. T squared plus your initial v velocity is your initial speed, times t plus your initial height. The final height, if it hits the water, would be 0, equals -16. We don't know the time, so we're going to solve for that. T squared plus, if you drop it, the initial speed is 0, so 0 times t. Plus, we know the initial, or the, so S is final height, H is initial. We said it was 220 feet. So we simplify. 0 equals -16 t squared plus 220. Subtract 2. So now this is just what we were doing a second ago. Get the numbers to the same side, get your squared item all by itself. -220 equals -16 t squared. Divide by -16. Divide by -16. 220 divided by 16 is 13.75 equals t squared. Take a square root of each side, and the square root of 13.75 is 3.71. You don't need to write plus or minus because there's no such thing as a negative time with this application. So it would take 3.71 seconds if you were to drop it off the Golden Gate Bridge for it to plunk into the water. And that is it. Thank you very much. I'll zoom that back out so you can see it, and have a good day.